Okay, yeah, so it's Pablo Maier, and you'll be telling us about why the Attoclock does not detect tunneling time, right? So
Exactly.
take it away.
Okay, so I'm going to talk about tunneling times from TiQT ionization, and hopefully we will all understand why we think that the Attoclock does not detect tunneling time. First of all, the people who are doing this project with me are these. They're all very helpful, and she's been my supervisor for my master's thesis, and now also for my PhD. Okay, so what is tunneling time? If we have an electron incident on the barrier, we know that it quantum mechanically can go through, even though it doesn't have enough energy for it classically. By tunneling time, we mean the time that the electron spends inside of the barrier. Like we all know here, because there exists generally no self-adjoint time operator, historically there's been a lot of different definitions of tunneling time, and they all don't necessarily agree. Recently, this topic has been revisited in the context of TiQT ionization because of the accessibility to the resolution of ultra-short timescales due to upper-second pulses of light. So, how does an electron tunnel in TiQT ionization? You can see here as a dotted line the binding potential of an atom, and there's a single electron specificity sitting in there. As a dashed line, you can see the potential created by an electric field. And in black, you see the potential that's created by the joint potential. And you can see that there's a barrier through which the electron can tunnel through. This means that even if we drive the atom out of resonance, we can get ionization because the field is just so strong. The electron can tunnel, yes. And historically, tunneling time was used like this. So the electron starts to tunnel at a complex time. It then penetrates the barrier in imaginary time, and then when it exits, it continues in real time. How does this make sense? The kinetic energy, the energy below the barrier, is negative. Thus one can argue that the velocity is imaginary. Since the displacement is real, time is imaginary. Okay, how can we measure tunneling times? I'm going to talk about two experimental setups. The first of them is the Llama clock, which has been used to measure tunneling time in scattering. And the second is the Attoclock, which measures tunneling time in strong field ionization. I'm just going to show two experimental results from the past to motivate you, and then I'm going to explain how these clocks really work. So here's an experiment of the Llama clock. So it's the time an electron spends in an optical barrier. And we can see clearly, so the red dots are the measurement with the barrier, the blue ones are without a barrier, and we can clearly see there's a time delay due to the tunneling through the barrier. Okay, so Llama clock measures tunneling time delay. What about the Attoclock? And I will explain it in more detail later, but just believe me at the moment that the angular offset is supposed to be measuring the time delay or the tunneling time, yes. So, here in black we have an experiment. So a measurement in hydrogen, and as the circles, blue and red, two different numerical calculations from two different groups with a Coulomb potential. So it seems that the Attoclock measures the tunneling time delay in hydrogen, but if one repeats the numerical simulations in a Yukawa potential, which is short range, suddenly one gets no angular offset. Thus it seems that we cannot attribute this angular offset to a time delay. This means it seems that the Attoclock really does not detect the tunneling time. So what's the difference between these two clocks? Why does the Llama clock detect the tunneling time while the Attoclock does not? Let's understand how these clocks work. Okay, so in the Llama clock, I think maybe most of you might know this, we have an electron with a spin. And then inside of the potential barrier, there's additionally a magnetic field. Inside of this magnetic field, the electron spin can precess. When the electron is transmitted and we measure the spin, we can thus, knowing the Llama frequency, infer the time the electron is spent inside of the barrier. Yeah, I forgot to. Yes. So the tunneling time gets mapped onto the spin angle. We can interpret the Llama clock as an example of a weak measurement what is a weak measurement? The weak value of an operator, this expression, and it can be measured by preparing a system in an initial state psi I, then performing a von Neumann measurement on the observable A, and then before reading out the measurement device, we post-select for states psi I. So let's see how this works in the alarm clock case. There's an electron, we prepare the electron with a spin, so this is initial state. Then the spin basically acts as a pointer that measures out the width of the barrier, and the post-selection is performed by only measuring transmitted particles, so we don't measure the ones that are reflected. In this sense, the Larmor clock can be interpreted as a weak measurement. Realizing this, we see that we don't really need to refer to any spin to calculate the Larmor time. We just take the inverse momentum of a plane wave, and theta b is just the projection onto the barrier region. This means that this integral only goes over the space of the barrier, and J is the probability current. With this we can just, for us to look at it, calculate the Larmor time for a Gaussian potential barrier. So in black you see the barrier, and you see this is not the time, it's the time density of a space. So if we would integrate over a specific region of space, we would get the Larmor time accumulated in that region. The two lines here show the classically forbidden region. We see that the time essentially gets accumulated towards the edges of the barrier. And what could seem kind of worrying is this kind of oscillatory nature of the Larmor time density, which should be related to the inverse velocity outside of the barrier. But this can be fixed by considering.
Oh, that's my bad. Okay. Okay.
Yes. Well, I'm going fast, I think. Okay. I'll explain when it's nervous. So this can be fixed by not using a single plane wave, but by using an entire wave packet. And then we see that outside of the barrier, we get a nice constant velocity. And inside the barrier, basically, the same behavior holds. Okay. So now that we understood the Larmor clock, we can think about the Attoclock, which is maybe, I think, more new to all of you. So the Attoclock uses a short pulse of certainly polarized light to ionize an atom. You can see here the binding potential of the core, and this slopey shape, the plane, is the potential created at a moment in time by the laser field. So additionally, because it's certainly polarized, this plane will rotate in space. But not only that, because the laser pulse is so short, there will be a specific angle where the magnitude of the field is the biggest. So you can see, let's say this is the time 0. So you can see that the barrier is the thinnest during this time, and then before and after, the barrier is much, much thicker. So the electron will tunnel, most likely tunnel, at time 0. And did everyone, well, else I would have done like the reverse. I'm very nervous by this. Okay. So yes, short circularly polarized light pulse, emission at the peak of the field. But how does now this time of ionization, now that we understood the tunneling part, how does the time of ionization relate to the angle of the photoelectron distribution? So if the particle would tunnel out instantly at the disorientation of the electric field, so in general, the momentum of the particle has two components. It has one component that goes with the vector potential with time, and then there's like a drift momentum. When we measure, when the laser pulse is over, we will never measure this momentary part, but we will only measure the drift momentum. And this drift momentum depends on the orientation of the electric field at the time of ionization. So if the particle, if the electron tunnels out immediately, it will drift off horizontally. But if it will take some time to tunnel, the electric field will have rotated a little bit, and it should drift off at an angle. That's basically the idea. So from this one says that the time of ionization gets mapped onto the angle of the spin. If we assume additionally. So in a sense, we get time of ionization, not the tunneling time. We need some assumption, and usually the assumption is that it starts to tunnel at time 0. With this together, we can infer the tunneling time. Okay, so this is the same which I just explained again, but here you could see like how this is a numerical experiment, but still how this photoelectron distribution would look like in hydrogen, and you can see that there is definitely an angle. But I remind you what I showed in the beginning, that no angular offset can be detected for a short range potential, meaning that when interpreting this experiment in hydrogen, one really needs to realize what is happening here and what corrections need to be accounted for. So the problem is that the angle of the momentum is not only affected by the time of ionization, but there's other effects due to the short envelope of the pulse and due to the Coulomb potential still interacting with the electrons. That's why in the Yukawa potential you don't get this. This means that when reading out the Attoclock, one can infer the time of ionization not only from the angular offset, but one needs to subtract the effects that I just said. Okay. So we will try to compare, look at a simple one-dimensional model of ionization, and maybe first see how the Larmor clock, if the Larmor clock would even detect the time in this case, because if it doesn't, there's nothing to know. Okay, so we start from the ground state of the delta potential, and then at time 0 we branch to this potential, so we just turn on a constant field. And we take the time, and we calculate the strong field approximation, and we take the limit t to infinity and get a stationary state. Okay, what is the strong field approximation? I think probably many people don't know this. So to solve the Schrödinger equation of this Hamiltonian, it's not as straightforward because we cannot use standard perturbation theory because neither of these potentials is small. But there's a trick. So first of all, we can still split up the Hamiltonian. We call this part H0, and this with this, it's the Hamiltonian for the propagation in the laser field. So this is still analytical solution, it is exact, where U0 is the propagation in only the Coulomb potential, and this is the propagator for the whole Hamiltonian. So we can read this like this, going from right to left. We start in the ground state, the electron just happily evolves in this potential where it's the eigenfunction, no? And then at time t prime, it suddenly feels laser potential and starts feeling the full force of the whole Hamiltonian. With this kind of interpretation comes the approximation that we say, okay, because the field is so strong, after the electron is kind of ionized, we only consider the laser field, the propagation of the laser field. And this is essentially the strong field approximation. And this is kind of good for short range potential. So this is justified. There's other ways to justify this in a better way. You can get the same results. This is more like intuitive. Okay. So I don't want, if we project onto plane waves, we can write the solution in this way, and I don't really want to you to care about the details, just that this phase is highly oscillatory, and that will be important in this range. So how does this look? Here should be B, so this is the energy of the potential, and this is the solution, how it looks. You see kind of full the bound state staying here, and then acceleration, the free electron is accelerating in the constant field. This is basically a superposition of every functions. Okay. This is a different representation of the same wave function. This is called the Lucini distribution, and it's related to the Wigner distribution. It's basically the wave function in phase space, so it's position, this is velocity. And what's very remarkable is what I've plotted here in blue is basically the classical trajectory of an electron starting with velocity 0 at the exit of the barrier. And we can see that very soon, being a little bit outside of the atom, if we are only interested in where is the electron, this is a very, very good fit. Okay. So, having this wave function, we can calculate the Larmor time with the weak value formalism, and we see that the Larmor time again, first of all, there is the Larmor time, and the Larmor time gets accumulated towards the edges of the barrier, just like in the scattering case. Okay. So now, is maybe a good time to introduce you to saddle point times, and you will also understand the historical interpretation of this complex tunneling time if you get this. So we have this solution in strong field approximation, and we have this highly oscillatory phase, and we can, the point is that if we integrate over it, most of it will cancel out due to the high oscillation. So we're looking for a place where the space basically becomes stationary, and only can say that only this contributes to the integral. Doing this is called saddle point approximation for highly oscillatory integrals. So doing this, we can do, one calculates the saddle point time and just writes the solution of the integral like this. And we can see that the saddle point time is complex. And this is basically where this picture is coming from. Okay. It was shown by Tolina et al. That the Attoclock actually measures the real part of the saddle point time. So we kind of cheat our way out of thinking in 3 dimensions and just simulate an Attoclock result in our 1-dimensional model by seeing how the saddle point time behaves. We can expand this integral around the saddle point, and yes, you can see that by taking the derivative of the argument of this function with respect to IP, so IP is the negative energy, so it's the ionization potential, you can see that we can extract the saddle point time. Meaning that now, if we evaluate this expression, disregarding this expansion, we kind of see how the saddle point time evolves as the momentum increases. So this is the Attoclock result. And we see that at 0 momentum, we get a positive value. And because of this constant acceleration of our model, we associate momentum 0 with the exit of the barrier. On the other hand, we see that the Attoclock time, it goes to 0 as the momentum increases. And again, because of the nature of our potential, we argue that this maps to the position of the barrier. And what one can really see if one looks at the wave function that, with very high momentum, one sees that this looks like a free wave function. This is what one always measures when one does an experiment. One measures on basically a free solution. Another hint will be is this calculation by Sergei Machkovsky. This is the 3-dimensional calculation of the hydrogen atom and constant electric field. And he calculated different trajectories from it. For example, the phase time and other trajectories. And what's kind of interesting, that although they may not agree at the exit of the barrier, when we move away from the atom, all the trajectories kind of go to the classical one. And this is not trivial. So this, I think this is kind of surprising. And from this we argue, okay, we cannot measure the time delay by measuring the time that has passed somewhere outside of the atom. We asymptotically, we really need some kind of positionally resolved measurement under the barrier, and that is what theoretically the Larmor time does, because the spin stops processing. If this is really experimentally viable, I don't know. But yeah, so what have we learned? We need to distinguish local and asymptotic times. We've learned the local Larmor time measures the tunneling time, that the asymptotic times fail to measure tunneling time in our model of ionization. And we've seen that the Attoclock actually measures the asymptotic phase time, which is 0. So we argue that to really be able to measure the tunneling time delay, positionally resolved measurement of the barrier is needed, and that's why the Attoclock doesn't detect the tunneling time, because it measures the momentum space, and that is not good enough. Okay, thank you for your attention.
Lots of time for questions. Please.
Hi, thanks a lot. I wasn't sure to have correctly understood when you start to measure the time in the Attoclock. Is that the moment where you turn on the laser and you are creating the electric field and the thing that starts turning? Because if I understood correctly, you know how to infer the time it took until it tunneled from the phase that accumulates by measuring the direction which it goes. I wasn't sure to understood when you start the measurement.
Maybe I was going too quick. Obviously, I only took 20 minutes, so it was very too fast. I think how the idea came up was because in this field, this semi-classical thinking is very successful, because like usually people treat like very large atoms and you don't get as far with exact quantum mechanical treatment. So these kind of semi-classical models with like real trajectories outside of the barrier, they became very popular. But I think this is a place where it breaks down. So what people think is, or how you can imagine it, is that the tunneling happens quantum mechanically, but once the electron is outside of the barrier, you start to calculate it classically. And then you can, from conservation of canonical momentum, so that would be P minus A of T. So this is also the momentum at time of observation, minus, it's not very pretty, is equal to P of Ti minus A of Ti, okay? This is just conservation of canonical momentum. And then, since the laser pulse is short, this is 0. And as you see in the Fushimi distribution, where was this? Later. You can assume kind of that the electron starts with 0 momentum. So you say that this is also 0. So now you see that, okay, this is a P, that the time, that the momentum at time of observation really relates to the orientation of the field at the time of ionization. But this is kind of, so this is how people came up with it. But what I think is that this is just, in general, not sufficient to think. So the semi-classical thinking is good when you make, when you talk about something that happens here, but you can see that this model kind of fails to capture the picture here. So I think that's where it's coming from. But I think, yeah, I think it's just not, yeah, it just doesn't work. Did that make sense?
Yeah. Yeah, Tom, go ahead.
Just kind of carry on that theme then, it's an experimental question. So the way I've understood this is that your time kind of starts when the field is strongest.
Yeah.
And you make it from there. So is it easy experimentally to make sure that the angle in your lab frame is always the same at the point where certainly parallelly is spinning around?
That is a very good question. Because I'm not an experimentalist, I cannot answer it very well, but I can refer you to the original paper. Yeah, I cannot answer very well, but there's a trick, and they use somehow circularly polarized light, and there's some sort of technique so the field doesn't actually always go into the same direction, but they have like some way of accounting for this so they know how it was pointed after the measurement. So they don't really align it, but they kind of know how it was. Does that make sense? I cannot tell you more.
It makes sense. Okay.
Yeah, I can give you the tape. I can refer you to the paper.
Yeah, Michael, please.
Yeah, a very quick one. So in theoretical derivations of tunneling times, one often finds that the tunneling time can be negative. And here it seems, I just kind of dawned to me now that we were talking about that in this ionization treated as tunneling, kind of never comes out like that. Can you comment.
That the tunneling time ionization never comes up negative?
Yes. So
And why that is? That is a good question. I don't know. I'm sorry.
anyone?
I'm really sorry. But
Why not tunneling time never shows up?
no, I'm just.
Maybe shake. Thanks.
Okay, any last question? If not, let's thank Pablo again.